All right, welcome to our review of the FARML 2022 questions. We're going to start off with the individual round, and then we will take requests at that point. So the chat window is going to be on the whole time for students. And in fact, I would encourage the students to kind of join in with the chat window. We do have the microphone function disabled. Because we want to make sure that it's for privacy reasons. Basically, when this thing goes up on YouTube, we want to make sure that we don't have any unauthorized audio from people who have not already implicitly given their consent to be on the audio. So students, you can chat though, and that will not show up on the YouTube video, but all of us moderators will see it. Feel free to chat requests to problems, especially after we finish the individual round. And then, of course, if you have some ideas about how to do some of these problems, maybe a different way than what some of the coaches have shown, that would be great. Feel free to chime in if you want. Okay, so you'll see on the screen that I have the opening page for this year's FARML document. Again, the entire document is in the shared team folder for the May 22nd practice. I do want to point out that we have in the room with us today myself, Liam, and Taman, who were all present at our practice on Sunday and will be with the team at ARML. We also have Tanula with us today. Hi, Tanula. Glad to have you here. Tanula is a mathleague staff member and will be coming to ARML as well. Probably with the SFBA team, but we kind of all hang out together anyway. I do want to point out that if you look closely on the page that I'm sharing right now, Tanula's name is actually there. So it looks like he had some role in shaping these questions. Tanula, tell us a little bit about your involvement with this process this year.
So basically, I was one of the reviewers, like some of the others listed. So Andy basically sent us the problems, I think like early in April, and we sort of reviewed it. Looking at the final questions, there were some noticeable differences. I think that the individual questions that Andy originally set were a bit harder than in the final package. So he did some shifting around and moved some of them onto the team. So that was pretty interesting to see. But as always, my favorite part of this is just trying to solve some problems while I'm also helping out Andy polish up the questions as well.
Awesome. Thanks for your help on that, Tanula. And I should also mention Tanula does the same sort of work for a bunch of other contests as well. He mentioned to me that he was helping out with math counts this year as well. Thanks Tanula for all your work on that. You'll also notice one other name on this page, and that is Silas. Silas is one of our coaches for both Wild Wild West and the San Francisco team. In fact, he handles a lot of logistics, travel arrangements for both teams. So you'll definitely see him at ARML this year as well. Okay, so let's go ahead and get into some of the problems. Let me move down to the first page, and I'll create a little bit of space here. All right, coaches, anybody want to jump in on this first one and get the ball rolling? I do have the annotation feature enabled so that you should all be able to mark up the document.
Yeah, I can jump in for a little bit.
Cool.
All right, so for I1, so read the question. If A and B are positive integers for which 20A has 20 divisors and 22AB has 22 divisors, compute the least possible value of A plus B. Okay. So when we see divisors, this is immediately a number theory problem. So we should prime factorize first, so you actually see what we're working with. So 20 here is just 2 squared by 5 times some number A. Then 22AB, 22 is 2 by 11 times A times B. All right. And we know that this is going to have 20 divisors. This one will have 22 divisors. from here, we kind of just had to kind of experiment and guess and check, sort of. And what you'll find is that there's actually, since 20, we have 22 divisors for this number 2 by 11 by A by B. And we know that 22 is also 11 by 2. And we know that for some prime factorized number, we know that the number of divisors in this number is k1 plus 1 times k2 plus 1 all the way to kn plus 1. And since 22 is 11 plus 2, it can't be 22 22 to the first, because there's actually more than one prime factor in this prime factorization. So we can rule this option out. So we only must have 2 prime factors here. So A and B must be some form of 2 to the A, 2 to the M, 11 to the N. So that's going to be the form of this number, where M and N are non-negative integers. But we see that in the other number, this has to have 20 divisors. So A, that means that A has to be a power, must exclusively be a power of 2, because if we introduce this 11, this power 11 into A, then it's going to multiply to have more than 20 divisors. So A must only be a power of 2. So from here, since A must only be a power of 2, this is 5 to the first, and we need to find some number P, let's say P, or let's do T, such that T plus 1 times 1 plus 1 is going to be 20. So T plus 1 is 10 and T is 9. So that means we get 2 to the 9 times 5 to the 1 to be this number that has 20 divisors. And so that means that A is going to be 2 to the 9th over 2 squared, which is 2 to the 7th. I'm going to box that for a little bit so we can organize so that we know what we have to do at the end. And since A is 2 to the 7th, we can just plug it in here for A times B, 2 by 11 times 2 to the 7 times B. And we need that to have 22 factors. So 2 to the 8 times 11 to the 1 times B. In order to minimize A plus B, we know that A has to be this, so B has to be as small as possible. We already have 2 to the 8 times 11 to the first. If we have 11 in there, then if we have an extra factor 11 there, that means we would distort whatever the 11 by 2 factor here. So we need 2 to the 10 by 11 to the first to get 22 factors. And so B is going to be 2 to the 10 over 2 to the 8, which is 2 squared. And so now we have A plus B, 2 to the 7th is 128, 2 squared is 4, and your minimum value is 132.
Cool. Yeah, let me just or kind of recap this a little bit, right? Because this, so first off, this thing down here that Toman mentioned, very important for you to know, right? So you want to, and in fact, if any of you are interested in why this is true, in terms of finding the number of divisors for something, just feel free to put that in the requests when we start taking requests later on, because I've got kind of a quick demonstration that I can use to show you why that's true. But yeah, once you know that that this is how you find the number of divisors, then you know that well, if we've got 22 divisors, then it's either going to be something to the 21st power, which Taman said it can't happen because we already know there's at least 2 primes here, or it's going to be the 22 is 11 times 2, which gives you the 2 means it's 1 prime to the 1st power. The 11 means it's a prime to the 10th power, right? So in other words, that basically tells you that this 2 times 11 times A times B is going to be something to the 10th times something to the 1st power. And then from there, you can just continue out and figure, do all the stuff that Taman did to find out what exactly those powers are. and get yourself to an answer. So thanks, Saman. Let's go ahead and move to problem number 2. So let's see here. I guess I'll go ahead and take that one. For one thing, it's straightforward enough that this will be an opportunity for me to kind of figure, for me to test my system here. I've got a phone that I'm going to be using the touchscreen for to do the problem. So let's see how this works. All right. So with number 2, basically what we're looking at is, and you're going to want to look at this and realize pretty quickly that, hey, this is a fairly straightforward problem. All right. Now, what this does for you in terms of ARML strategy is it means that hopefully you've glanced at both problems as soon as the timer starts. You look at number 2 and you realize, oh, as long as I know enough stuff from algebra 1, I'll be able to solve this, and there's not really much that's going on here. All right, so so what I would say strategically is you probably want to go ahead and start with problem number 2, get an answer for that as quickly as you can, move on to number 1, because by the time you're done with number 2, that gives you an indication of how much time you have available for number 1, right? And in some cases, knowing how much time you have available for a problem, especially if it's for one problem, right? You've already boxed away that other problem, and that's done. Now you have one problem left and a very specific amount of time. That'll help you gauge how fast you have to work in some cases. Now that's obviously not an exact science, but you get a feel as you go along for how long problems take and that sort of thing. So yeah, do number 2, then do number 1. And of course, if you are quick enough to be able to do both of these in a reasonable amount of time, then I want you to finish out by checking your work, right? So the deal is you've got 10 minutes to work on these 2 problems. You might as well use the whole 10 minutes, right? Because you'd be surprised how often it happens that you got 2 answers. Wonderful. Maybe in 4 minutes. Okay, I got my both of my answers. You keep working on it and you realize with like a minute to go, oh, I made this small calculation error. Let me just clean that up real quick and save myself a point. All right. And if you had just like zoned out after 4 minutes when you got the 2 answers, then you would have wasted a chance to get that point. So understand, of course, that happens surprisingly often. And there are a couple of things that you can do with these problems in order to use that time wisely. Right? And I'm specifically talking about that within the context of these first 2 problems, because a lot of times people can get the first 2 answers a little bit faster as a pair than they can most of the other pairs. So I think it bears some emphasis on the strategy there. All right, so the other thing that you would do as far as checking your answers, I often recommend one of 2 solutions. One thing would be that's kind of a generic idea that always works. If you can find a second solution method, would be to solve the same question a completely different way than you did the first one, or the first time, because at that point, then you've got you've arrived independently at the same answer 2 different ways. This is basically like what we do on the team test when we check each other, when we have 2 people working on the same problem. They might have used the same techniques, right? But we've got 2 completely different individuals, and it's much less likely that the same mistake is going to get made twice. On the other hand, if you check your own team test problem, you're probably going to get, if you make a mistake, you're probably going to make the same mistake the second time you do it. Similarly, if you try to do a problem the same way as you did before, if you made a mistake the first time, you might make the same mistake the second time. But if you have 2 completely different solution methods that, maybe you made a mistake over here, well, there's not even that chance to make that mistake on the other one because you haven't even done the problem that way. All right, so with that in mind, let's take a look at number 2. And I'm going to mention here, I know Tanula sounds like he's got some pretty advanced familiarity with these questions. On the other hand, I'm looking at most of these questions fresh, right? I glanced at them for a couple of seconds when I put the pages up on Sunday, but other than that, I'm just kind of looking at them for the first time. And I think that's helpful in one of these situations, because then I can kind of walk you through what to do. So getting into number 2, f of x is a straight line passing through 2 points. Okay, great. So we know that we have everything we need to know about f of x right here, right? If I have 2 points, I've got a line. So basically we know that f of x is going to equal, it's going to be of the form mx plus b, right? You all learned this in Algebra 1, so none of this should be surprising. We just have to figure out what f is. So first off, we're going to look for a slope, and I see that usually what I'm going to do is take, to find the slope, we're just going to take the difference in y, so 143 minus negative 25. Be careful about that. That's where I think the most likely point at which you would make a computational error comes in. So, you might take 143 minus 25, 118. But no, you have to do 143 minus negative 125, which means add them together. And I'm going to ask my assistant coaches to check my work on these, right? Because I'm getting a 168 for that. But feel free to just chime in if I make any computational errors here. And then we look at our change in x. So I'm going to take, going the same direction, I take 73 minus 97. Keep in mind that will be a negative number then, and we're going to get a negative 24. Now, the good news is 168 divided by 24 is an integer. So we're going to say here that f of x, 168 divided by negative 24 happens to be negative 7, by the way. So f of x is negative 7x, and then we just have to figure out what the b is. All right, so if I take either one of these points, 73 comma 143, for instance, and I take negative 7 times 73, I believe that gives me a negative 511. And then plus b, that will give me a 143. All right, so I just have to, and that should be an equal sign there. I know the, let me just draw an extra line so it looks more like an equal sign. All right, so now I know what b is. Just going to be 143 plus 511. So that's going to be 654. Okay, so now that I know what f of x is, then I can double check that this is the correct formula for f of x if I wanted to. And I'm going to divert from the problem for just a moment to go back and talk about the strategy of checking your work. Right? If you wanted to right now, you could plug in the 97 negative 25 just to be sure. All right, 97 times negative 7 is going to be, I believe, negative 707 if I'm not mistaken. Let me just do that calculation again because it sounds wrong. Negative 600 and where am I here? Let's see. So the 90 times negative 7 is going to be negative 630. 7 times negative 7 is a negative 49. So it's negative 679. Okay. And then I'm going to add 654 onto that, and I do get negative 25. Okay. So I've verified that this equation works with the first one because that's actually where the equation came from. And then also with the second one by plugging it in. Now, as far as the strategy goes, I mentioned earlier that one possible way of checking your work on a problem would be to do the problem from scratch a completely different way. Another way that you can check your work on a problem for certain problems is you can plug in the answer or a step that leads to the answer and verify what's going on. And I'm going to refer back to problem number 1 as an example for that. Compute the least possible value for a plus b. I guess I should mention that if they said that there is only one possible value for a plus b, then you would take your a, you obviously have an a and a b in order to figure that out. At least from this problem, you would plug an a and a b into the numbers, right? So 20 times a, 22 times a times b. You'd calculate how many factors they have. You'd verify that it's 20 and 22 respectively, and that would be a good check on your work. Now, when it says the least possible value, you can't just plug in one value and say, oh, look, that value works. So that strategy of plugging in may not work so well. But for this one, number 2 should be very easy to go ahead and plug things in at the end, or even as we go along, as you've seen me do here. All right, so now that we've got this, it's just a matter of plugging it in, right? So we have f of 22. And then we're going to have So we're going to subtract f of 20, but we can go ahead and plug in f of 22 at this point. So what's f of 22? Negative 7 times 22 is going to give you negative 154. Add on to that 654. And this is inside the parentheses, right? So the f of 22 is what's going to go inside the parentheses here. So I've got my negative 154, and I add 654 onto that, and I'm going to get a 500. Okay, and then I have f of 20. So I'm going to take that f of 20 and put that inside these parentheses. If I plug in a 20 into this, I get negative 7 times 20 is negative 140. So it's basically 654 minus 140, which is 514. And then, of course, I just have to process both of those. 500, if I multiply that by negative 7, I get negative 3,500. Add 654 onto that, and I should get negative 2846. Somebody check my work on that. For the 514, I could plug in a negative 7. I've got negative 3598. I'm actually going to write this one down because I don't know if I can do all that in my head. Negative 3598 plus 654. Okay, so I'm going to use a number sense trick that I share with my elementary students to deal with this. I'm going to add 2 to both of these. All right, so it's good to have some computational tricks up your sleeve for these sorts of things. All right. Actually, I'm going to subtract 2 from the negative 3598, which is negative 3,600. So notice that I bumped that one down by 2, which means I got to bump the other one. Something happened on my phone. Okay, there we go. So if I bump the one down by 2, then the thing I'm adding has to be bumped up by 2, which is going to give me a 656. So what if I got 656 minus 3,600, which is basically 56 minus 3,000, which is negative 2944, I believe. Did I seriously write 9244? See what can happen when you're writing these things, right? Even if you know what you're doing, sometimes you just write the wrong thing, or sometimes you make a mess with your handwriting too. So that should say 2944. All right, and what am I supposed to do here? I'm supposed to subtract those from each other, right? So basically, I've got negative 2846 minus negative 2944, or just 2944 minus 2846, which should give me 2944 minus 2846, which should give me a total of 98. All right, coaches, how did I do on that? Did I get the right answer first? And I have a follow-up question that I want to see if any of you have an answer to on this one. My follow-up question is, does anybody see something else we could do with this problem? All right, I mean, this is straightforward, right? What I just showed you was an Algebra 1 approach to this problem, assuming that I didn't make any errors anywhere, which, by the way, you'd be surprised how frequently your errors come into straight up calculation problems, right? So in other words, you might end up, with a problem like this that's possibly, I haven't seen the rest of the question. I'm guessing this is probably the easiest question out of all 10 of them, right? I'm also guessing this is the easiest question to get wrong if you make a silly mistake, right? Because you're likely not going to make a mistake on some sort of higher level mathing as easily as you would just doing some subtraction wrong. All right, so that's something to be aware of, and something you really, that should be a red flag in your mind. You want to go back and double check your work on this one for sure, just to make sure you haven't made a calculation error. All right. So Marcus is telling me f of a minus f of b equals negative 7 a minus b. I want to take a look at that, right? So what we're doing here is, okay, let me get my phone situated properly again here. Okay, so we already figured out there's my annotation. All right, we already figured out that f of x was equal to negative 7x plus, what was that other number? Was it 654? Okay, So so what we want to do here is take, if we just start with that, we've got f of 22 minus f of 20. All right. So what Marcus is saying is that we can basically take out that -7, right? So let's say that I had f of I don't know, f of 6 minus f of 3, right? Look at what that does. Or better yet, I could just do the a and the b thing like we have in the chat, because I think that might even I mean, we just do that straight up with the variables. F of a minus f of b. Well, what is f of a? That's going to be -7a plus 654. And then f of b is -7b plus 654. And if I'm going to subtract those two things from each other, then what I end up with is -7 times a minus b, right? So I factored out a -7 from, well, I can factor out -7 from the whole thing, and I've got an a minus b, and then the 654, whether you factor out a -7 or not, the 654s are going to cancel. So you have -7 a minus b here, right? So that's a shortcut that I wanted you to see, and I'm glad that Marcus identified that, right? So what we have now is, if I want to subtract these two things, then it's really just going to be -7 times a minus b, which is a lot easier, right? So if I wanted to do f of 22, then minus f of 20, then that's going to be -7 times a, which in this case is f of 22, minus b, which is f of 20. Okay, hold on a second. We can do that same trick again, right? So now that we have an f of 22 minus f of 20, we can replace that with our negative. So inside the parentheses, I can replace that. Just a moment, my phone is acting up again. All right, inside the parentheses, we can replace this with a -7 times a minus b, which is 22 in this case, minus 20. All right. Now, I want you to notice this is effectively a completely different way of setting up the problem than what I did before, but we're going to get the same answer, right? 22 minus 20 is 2. Multiply that by -7 times -7, which is the same thing as 7 times 7. 7 times 7 is 49, and double that to get 98. Same answer as we got before. All right. But I want you to see how much simpler this is. Now, what we, in fact, notice a couple of things. First off, this is much simpler. If you recognize this this property of what's happening. Now, how would we think of Marcus's property? I've got a couple of answers for that. Number one, you might notice that if I were to the whole problem is about subtracting two pieces. If I were to subtract these two pieces, then given the fact of how the formula is set up itself, I've got this constant part. And if I'm subtracting that from itself, right, from two different iterations of the function, it's going to go away. So you might be thinking along those lines, hey, I bet there's some simplification that can be done. That's your motivation for testing out what is f of a minus f of b. All right, so if you think of that, great. And hopefully I've just given you some motivation to think of that. If you don't think of it, you can still do the pure algebra 1 approach, which is just plugging it in and bashing it out. All right, now, obviously, if you, and this is a good idea, or this is good advice for problems in general, right? Is that a lot of times there is a clever shortcut, which is to do this little substitution and make things a lot easier on yourself. And the other thing is that if you can't identify a clever shortcut, you can just go with the long method, or the obvious method. So I would say, you know, for most problems, see if you can find a little shortcut, and if not, just go ahead and do what you know, right? I mean, anybody with an Algebra 1 background can solve this problem, but if you apply a little bit of thinking to it, you can make it so much simpler. I also want to point out here that it looks like all we need is the slope, right? Because once we'll take a look at that 654 up here, right? If I had just turned that 654, I'm going to put a circle around it. We'll just call it B, right? The y-intercept. Okay, if I had done that, well, that B shows up here, that B shows up here. Again, I don't even know what the 654 is, but once I subtract them, I'm just left with negative 7 times A minus B. The 654 goes away. So this is one more shortcut, one more advantage that you could have achieved by identifying this formula that Marcus showed us, which is that that we don't even have to find the B, right? As long as you find the slope, the rest of it kind of falls right into place. All right, cool. So let me clear things out, and I'm going to move over to the next page here, and we'll see what we can do with that one. All right, number 3. Do I have a volunteer from among the coaches to do number 3?
Yeah, I can take number 3.
Awesome. Go ahead, Liam.
All right. So we're starting with a convex quadrilateral ABCD. I'm going to just do some drawing right here, get a vague general shape. I might adjust it as necessary. And I'll label all the points I need. A, B, C, D. AB is 4, and I'm going to write that the tangent of angle A is also 4. I don't really have a good way to write that down in the diagram, no right angles or anything like that, so we'll just keep it here for a bit. BC and CD are equal to 9, and AD and BD are the same, so I'll just do the little congruent tick mark. And what we're being asked to find here is the area of ABCD. So one thing I noticed pretty quickly is I've got one isosceles triangle here with ABD. I've got another one with BCD. So if I can somehow translate it's my tangent A into some side lengths for AD and BD, I'll be able to get either heights and altitudes or more angles. I'll have enough information to calculate the areas from there. So let's start with triangle ABD. So draw like this. So D will be the apex. We have B, we have A. And we're going to drop down the angle bisector. Useful fact about isosceles triangles, the angle bisector of this point, so it's a matching side, is going to be a bisector of the side AB. So I know that if I label this M, AM is half of AB, which is 2. And here, since tangent of A, that's opposite over adjacent, is 4, that means our height here has to be 8. We can then calculate, using Pythagoras' theorem, what this is. So we have square root of 2 squared plus 8 squared, which I believe is the square root of 68, which I'll simplify a bit further to 2 square root 17. We'll also note that the area of triangle ABD is 1/2 base times height. dm is the height to AB. So get 1/2 times 4 times 8 equals 16. Now let's take a look at triangle BCD. BCD. This is 9. This is 9. I'll drop my altitude again. Call this point N, and it's still the midpoint of BD. So that means if BD is 2 root 17, ND is root 17. And thus, CN, by the Pythagorean theorem, is the square root of 9 squared minus the square root of 17 squared, which I'll just write as 17. 81 minus 17 is 64. And thus CN is 8. So the area of triangle BCD, using the same 1/2 base times height, is 1/2 times 2 roots times 8. The 2's cancel, leaving 8 root 17. So we simply add the area of the 2 triangles together to get our final answer, 16 plus 8 square root 17.
Cool. All right. Yeah. So I want to point out something Liam said right at the beginning. I'm just going to start drawing, and I might modify my drawing later, right? And that is a great that's a great way to go about these things, right? I mean, you do want to, if you can, you sort of want to take a look at, you know, the big picture, what the diagram is ultimately going to be looking like anyway. You know, for something like this, you know, we do have a couple of congruent sides, so you might as well make them so they sort of look congruent. But you know, beyond that, as long as it's a convex quadrilateral, you should be able to mark it up in a way that's going to work for you. Dropping those altitudes with geometry questions, adding extra line segments is often a great idea, right? Liam mentioned that if you drop that altitude in that isosceles triangle, it does bisect the opposite side. You can get that from the angle bisector theorem, or you can just look at it from a symmetry perspective. But yeah, that makes things, the numbers worked out wonderfully here, which is nice. You know, obviously we could have, you know, we could have used Heron's formula for the area of any of these, but who wants to do something like that with a bunch of root 17s hanging around? All right, so yeah, great stuff, nice. And yeah, again, you know, you've got your basic geometry skills. It's just a matter of, you know, thinking through what to do. That tangent is probably the part that is going to intimidate some students. So I do want to address that for a moment, right? I would say with problems in general, right? Sometimes there's going to be something in a problem that looks, you know, like, oh, I don't want to deal with tangents, you know. You know, because, you know, okay, first off, when I look at a problem that has a tangent in it, all of a sudden, you know, I'm thinking, okay, you know, how much of my trig identities do I memorize? How confident am I that I can rederive one on the spot if I don't already know it? You know, and so I'm like, you know, starting to panic when I see a tangent in a problem. Turns out it wasn't that bad, right? As long as you know your basic definition of tangent. You know, as Liam demonstrated, you drop that altitude, you've got a right triangle, and, you know, tangents work beautifully on right triangles. So don't let that intimidate you. And as a larger strategy point, don't get intimidated when you see something in a problem that you're not sure of, right? Sometimes it's, you know, it turns out to be easy. It's not as difficult as you thought it was. There are times also when you see something in a problem when you just literally don't know what it means at all. All right. So I'll give you an example. Sometimes they will talk about a, they might have referred to this as a non-degenerate quadrilateral. All right. When you see something like that, the best approach I can, especially if it's an adjective, best approach I can recommend is ignore that word entirely. All right. If they had said that this was a non-degenerate quadrilateral here, basically it would have been that would have just been the test writer's form of insurance, making sure that that nobody's going to come back later and say, well, did you consider a quadrilateral that has 0 area? If you write in that it's if you account for that in your question writing, then it resolves any ambiguity. But that's one of those things that is probably not even going to be an issue for most people, right? So if you see an adjective like that that you're not sure what it means, most of the time you can ignore it and you'll be just fine. And I see this happen probably more with geometry problems than anything else. One last note on this one before we move on. I mentioned drawing lines, right? So in triangles, you want to be thinking about, how can I create right angles, for instance, like Liam did here? How can I, find similarities, stuff like that. With circle problems, you're almost always going to be wanting to draw a radius from the center of the circle out to any point where the circle intersects with something else, right? So, and dropping altitudes, creating right angles, that sort of thing, very helpful. All right, so let's go ahead and get rid of these. And who wants to do number 4?
I can try doing that one.
All right, cool.
All right, so it says that the third coin is to be tossed 7 times. Compute the probability that the first 5 flips or all 7 flips or both form a palindrome. And so, for example, HTT, HTH is one of those flips. And as you can see here, the first 5 flips here form a palindrome. So one thing first I want to mention is that they were actually nice to include the or both. One thing you want to remember is that usually, unless they say something like exclusive or something like that, if they just say or, that means you have to worry about what happens when both of them occur as well. So just something to keep in mind as you do those problems. Okay, so we have coins being flipped 7 times. So let me go ahead and make 7 slots for these coins. And let's focus on the first case where the first 5 flips are going to be a palindrome. So if the first 5 flips are palindrome, what this means is that the center is going to it's going to be centered around the 3rd flip, right? So for example, if you have an H and a T here, then that automatically determines what the 4th and 5th flips are going to be. It's going to be, the 4th one's going to be a T, and the 5th one is going to be an H. Right, and the 3rd one doesn't matter because this is an odd number of flips. So the 3rd could either be, for example, a head or a tail. So essentially what actually determines if this is a palindrome is if the 4th and the 5th flip are the exact same as the 1st and the 2nd flip. Right. So what you can imagine is you can think of the 1st and 2nd flip being any sequence you want. It could be head, tail, heads, heads, tails, heads, or even tails, tails. But once you flip those 2 coins, the 4th and the 5th one need to be fixed in order for this to be a palindrome. Right. So basically, once you have decided what the 1st and 2nd flip become, then the probability that the 4th flip is the same as the 2nd flip is going to be 1/2. And the probability that the 5th flip is the same as the 1st flip is also going to be 1/2. And since these events are independent, we multiply them together to get the probability of 1/4. So this means that the probability that the first 5 flips are all the same, or form a palindrome, sorry, is going to be 1/4. And you can employ the same thinking for the 7 flips, right? So in this case, let me redraw 7 new slots for the second case. So in this case, if you look at all 7 flips, this time it's going to be centered around the 4th flip. Meaning that, let's say we had a sequence HTH, then the only way for this to be a palindrome is if the 5th flip is the same as 3rd flip. So these 2 flips are the same. And similarly, the 2nd flip and the 6th flip are the same. And finally, the 1st and the 7th flip are the same. Right, so it's the exact same logic as the previous case. The only difference is now you have basically 3 flips that have to be the same as 3 other flips. Right, so again, you can think of this as, okay, you flip the first 3 points. It can be any sequence. So it could be HTH like I wrote here, or maybe it's something like THH. Whatever it is, you know that the probability that the 5th flip, so actually, let me just number these so it's a bit more clear. So the probability that the 5th flip is the same as the 3rd is going to be 1/2. And same with the 6th and 2nd flip being the same, and also the 7th and the 1st. And again, all of these happen independently. So we multiply these together. And that means we get a probability of 1/8. All right, so now we've done these 2 cases separately, but notice that if they both happen together, then we've actually overcounted that in these 2 cases. So what we need to do is we have to subtract now the probability that both of these 2 happen. Right, so let's look at one that happened. So let's redraw this. And so some of you might be familiar with what this technique is called. It's called principle of inclusion exclusion. And the short form I'll write down here is called pi. And essentially, whenever you see some sort of combinatorics or probability problem where you have to compute either the probability or the number of ways that something happens or something else happens, a good thing to think of is the principle of inclusion exclusion. So basically what it says is that you look at the probability that each thing happens on its own, and then you subtract the probability that both of them happen, right? And the reason is because you're overcounting the probability that both of them happen when you do the 2 cases separately, right? Easy way to see this is if you look at a Venn diagram. This, let's say you have event A for one of the circles, event B for the other circle. The probability that A or B happens is going to be this entire shaded region. And the way to get that is you look at this first full circle, and then you look at the second full circle. When you add those 2 together, you'll notice that you're adding in this common area twice, right? And that common area is the probability that both of them happen, which is why we subtract them off. So that's sort of a visual representation of what this principle is. And of course, you can generalize this to, not just 2 events, but multiple events. The formula gets more complicated, but the basic idea is just the same, right? You start off with doing them separately, and then you subtract for the overcount. When you have more items, once you do the subtraction, you'll actually be subtracting too much. So you add it back in, and so on and so forth, right? And those can also be represented with a Venn diagram. But of course, again, the more events you have, the more complicated the Venn diagram is going to look. So anyway, back to this problem now. So this time, this third case is we're looking at when both the first 5 flips and all 7 flips are going to be the same. So this is a bit more trickier, but we can still use the same general strategy, right? So we know that the first 5 flips have to be centered around this third flip. We also know that all 7 flips have to be centered around this fourth flip. So let's go ahead and just write out some sequence here. Let's say we have H, T, and because the third one for the 5 flips doesn't matter, for now I'm just going to say it can be anything. And let's see what we can deduce of the sequence so far. Oh, wait. Sorry, it's looking a bit weird on my screen for some reason. Let me just see if I can quickly erase some of this. Oh no, okay, it's better now. All right, so from the first 5 sequence or first 5 flips, remember that we need the second and the fourth flip to be the same. So we need this to be a tails, and we need the first and the 5th flip to be the same. So we need this to be a heads. And now let's see what we know about the rest of the flips, right? So remember, we need to have that all 7 flips form a palindrome as well, right? So that would tell you that the 7th flip has to be the same as the first flip. So that means we've already determined that this is a heads, and same thing, this is a tails, right? So essentially, the things that have been determined so far are going to be the 4th, 5th, 6th, and 7th flips. But if you notice, in order for all 7 to be a palindrome, we also need the 5th and the 3rd flip to be equal. So that means that this 3rd flip is also going to be determined to be the heads. So that one is also determined. So essentially what will happen is, let's say we flip the first 2 coins, right? Let's say we get a heads tails like this. What we first need is we need the 4th flip to be a tails, and that has a probability of 1/2 happening. We also need the 5th flip to be a heads here, that has another 1/2 happening. And then we need the 6th flip to be a tails, so we can multiply that by 1/2 as well. Same thing with the 7th flip to be a heads, we multiply that by 1/2. And finally, we need the 3rd flip to be a heads, so we multiply that by 1/2 as well. And sorry for all this extra drawing, I'm not sure what's happening. But essentially, what you realize is the probability that this entire thing happens, both the first 5 and all 7 flips happen in palindrome, is going to be 1/32. Right. And so in general, what you'll see with these different cases is that it's essentially going to be 1/2 to the power of flips that are essentially fixed once you decide on some number of flips, right? So in this third case, once we decided on the first 2 flips, everything else needs to be fixed in order for this to be satisfied, right? And because those things have a probability of 1/2 happening independently, when we multiply them together, that's going to be 1/2 to the 5 in the third case, which ends up being 1/32. And same thing with the second case, we saw that the 5th, 6th, and 7th flips are determined once we've chosen what the first, second, and third are. So that's going to be 1/2 to the 3, which ends up being 1/8. And same thing for the first one. So overall, the final probability is going to be 1/4 plus 1/8 minus the 1/32. Remember, we're subtracting the overcount. So let's do that subtraction. So this is going to be 1/4 minus 1/8. Or sorry, plus 1/8. And then minus 1/32. And so fortunately, these are all powers of 2, so we can just take a denominator of 32. And so 1/4 is going to be 8 over 32. 1/8 is going to be 4 over 32. So 8 plus 4 minus 1 is going to give us an answer of 11 over 32. And I'll just now write that down because I'll probably get duplicated again. But yeah, so you can sort of see the basic idea of this is, I mean, just to try it out. And what you realize is that once you've selected some flips to be whatever sequence they are, a lot of the remaining flips end up being fixed. And the number of flips that end up being fixed will affect your overall probability, which in this case ends up being 1 over 2 to the number of flips that will occur.
Cool. Thanks, Danula. Yeah, so I'll just add something in here real quick. Because the other way that I saw to do this one, and some of you may be thinking along the same lines here, is if you're really comfortable with the probabilities and the inclusion exclusion thing, you could totally do it the way that Sanula did. But one of the things that I was thinking here was, anytime you've got a probability problem, you've got a numerator, you've got a denominator, right? So one of the things you could do then is say, well, what's my overall denominator? And what I'm thinking here is you could do this by counting sequences, right? So that's basically the approach that I'm looking at. I've got 7 flips, which means that, each flip, there's 2 possibilities. So 2 times 2 times 2, 2 to the 7th, or 128 would be our denominator there. And at that point, then we could just calculate not so much the probability, but the number of sequences, right? So how many sequences have the first 5 that are a palindrome? Well, as we've seen, we have total freedom except for the fact that 2 and 4 have to be the same, 1 and 5 have to be the same, right? So I've got 2 choices for the 1 and 5. I've got 2 choices for the 2 and 4. And then I have 2 choices for the 3, 2 choices for the 6, 2 choices for the 7, right? That gives me 5 places where I have a choice, or 2 to the 5 sequences that I can draw out. All right, so that's going to be 2 to the 5, which is 32. Now, what I want you to notice is 32 over 128 is the same number that Tanula got earlier, which is 1/4, right? So we could do the same thing with our 7s and say like, well, I have to make sure that the outside ones 1 and 7 match, 2 and 6, 3 and 5, right? So I've got a choice here, here, and here, and then another choice in the middle. That gives me 4 choices, 2 options for each choice. That gives me a 16, and then I can subtract the ones that are both. Because you do still have to do the inclusion exclusion here, but I think there are going to be a total of 4 sequences that are doubly palindromic. Turns out, by the way, that if you look at what Tunu was drawing earlier, because of those axes of symmetry, that 1 and 7 have to be the same. And 1 and 5 also have to be the same, but 5 and 3 have to be the same. So it turns out that 1, 3, 5, and 7 are all the same. And similarly, because of the first axis, 2 and 4 are the same. Because of the second axis, 2 and 6 are the same. So 2, 4, and 6 are the same. So basically, once you've chosen 1 and 2, all the rest of them are fixed, right? So I have 2 options. That's why there's only 4 there. So you could do it like this: 32 plus 16 minus 4 over 128. You get the same thing, right? It all depends on whether you want to count, whether you want to be adding probabilities or adding numbers of sequences. And both of those are completely valid ways to do that. All right, so let's go ahead to numbers 5 and 6. All right, coaches, who wants to do number 5?
I can take this one.
All right, let's do it.
All right. We need to determine the triple positive digits ABC for which a factorial plus a to the b is ABBC. The digits ABBC. Well, we just list all the factorials because the factorial grows faster than the exponential. We can probably just mention those first. So, okay, wait. Okay, nice. So here,
Now,
1
Taman,
factorial.
Taman, when you're talking about that, you said you're talking about the factorial growing faster than the exponential. So I assume that you're looking at that factorial. That a factorial is going to be the kind of the dominating factor here, and you're
Yeah.
like, well, it's got to be a 4-digit number or
Yeah.
less. So that I think that that'll really constrain things. I like it.
Yeah. So we have this 1 factorial is just 1. We just list some factorials because it's going to grow pretty wild. 2 factorial is 2. 3 factorial is 6. 4 factorial is 24. 5 factorial is 120. 6 factorial is 720. 7 factorial is 5040. 8 factorial is 40,320. Oh, and then we can stop there because that's way too big. So we know that A has to be 7. So that means we can rewrite this equation as 7 factorial plus 7 to the b power gives you 7bbc. Right. So we know that this is going to be 5040 plus 7 to the b is 7bbc. So that means that this number has to be roughly 2000 to get the thousands digit to be a 7. Well, luckily we can just list the powers of b. See that it grows pretty fast as well. 7, 49, 343, 2,401, 16,807. Okay, that's too big. So that means that we see that it's 7 to the first, 7 second, 7 cubed, 7 to the fourth, right? So b is 4. And just adding 5,040 plus 2,401 gives you 7,441, which is A, B, B, C. C is 1, so our pair A, B, C is 7, 4, 1. We're done.
Good stuff. Yeah. So for this one, it's I think a lot of people are looking at, there is the student out there who's going to look at this one and be like, I've got to solve for 3 different digits and only 1 equation, right? How am I going to do this? Well, there's a lot of constraints, as Taman mentioned, right? As we can see, A cannot be larger than 7 because that's going to give us a number that's too big. Right? So, wow, that really gives us a small amount of numbers to work with. Now, I do want to point out that we have not proven that A can't be 6, right? So, if A is 6, I've got a 720 over here, and then I've got to have some A to the, then I'd have 6 to some power being a 4-digit number to get us into that 4-digit territory. It's not impossible. I mean, there are numbers that'll get you there. But the beauty of it is that this is a kind of question I was talking to you about before, contrasting with problem number 1, where it said find the least value of this. This one just says determine the triple. So if you find anything that works, you go with it, right? And so based on that, I think that I like Taman's approach. I mean, you could have started anywhere, right? A has to be 1, 2, 3, 4, 5, 6, or 7. Start anywhere, right? And once you have once you've picked an A, you can solve for a B and find out if it's an integer. And I think that starting with the 7 was a great idea. Taman found one, and we're done. We don't even have to test the others, right? Because they said determine the only triple. Now, if there were more of them that worked, then and they said find the triple that gives you the largest 4-digit number or the smallest 4-digit number or something like that, you might have to adjust your searching and come up with a little bit of intuition about how to demonstrate that you actually had the largest or smallest one. But fortunately, the test writer has already done the work for you. So I want you to pay attention to that from a strategic standpoint, because if they're promising you that there's only one, then all you got to find is 1 and you're done. So that was nice and straightforward. If you could just find that one pretty quickly, like Taman did. Excellent. Thanks. Let's do number 6. Do I have a coach to volunteer for number 6? All right, I'll go ahead and do that one then. Let me just get my setup here. Okay, so I've got an increasing arithmetic sequence of positive integers. So you want to to know what an arithmetic sequence is, obviously, so, right? So they're evenly spaced. And we got that the log of A1, log base A1 of A13 equals log base A13 of A125, which equals 3/2. Okay, so what I'm going to do is use a principle of logarithms here that says if I have log base A1 of A13, that's basically the same thing as a log of, that should say log of A13 divided by a log of A1, that's going to equal 3/2. And then similarly, I can do that with the other one. I can say that the log of A125 divided by the log of A13 is also equal to 3/2. Okay, and please note that I have three equations here, right? So because I have three equations, I can actually extract three pieces of information here. My third piece of information would be to set the left-hand sides of these two things equal to each other and find out that the log of A13 is the geometric mean of the log of A1 and the log of A25. We'll come back to that if we need it. Right. So basically this is how somebody might think about this problem, right? And again, I'm kind of, flying blind here and saying, well, what would I do if I saw this problem from the outset? Well, let's take a look at that first one. We find out that twice, if I cross multiply, I get 2 times log of A13 equals 3 times log of A1. I can bring those coefficients up into the exponents over here, right? So that's a power of logarithms that you might remember. Also, because these are positive integers, I know that the log of one positive integer equals the log of another positive integer. Well, first off, I should mention that because A13 and A1 are both positive integers, A13 squared and A1 cubed are also going to be positive integers. And if the log of one positive integer is the same as the log of another positive integer, we strip away the logs and we find out that A1 cubed equals A13 squared. All right, so let me just write that a little bit more nicely. A1 cubed equals A13 squared. Okay, now we can do the same thing with the second equation here. And let's see, I could say that I'm just going to jump straight to the end because it's the same calculations. A13 cubed is going to equal A125 squared. All right. So that now gives us something to work with. Now one of the things that I'm thinking of doing at this point is, so I look at this and I say, all right, I've got these two relationships between A1 and A13, between A13 and A125. I also had that relationship earlier that I mentioned, right? If I combine these two and set them equal to each other, then what I have is that the log of A13 is going to be the geometric mean of the other two logs. So in particular, let's see where that goes, right? So let's say that the log of A13 times the log of A13 equals the log of A125 times the log of A1, right? And I'm thinking at this point, well, that doesn't necessarily help me with the other part, right? So what I want to do maybe is to take a closer look at this relationship up here. All right. So this is the point where I'm going to throw it out to you all. What do you all see at this point that we could do here? So I've got this relationship that's saying that that the cube of one thing is the square of another thing. I could turn these all into, I could actually come up with a relationship between a to the first and a to the, A1 and A125. If I were to say, let's say we cube the first one, right? A1 to the 9th power equals A13 to the 6th power. And of course, if I bring that down to the second equation, by squaring those, I get A13 to the 6th power, which equals A125 to the 4th power. Okay, so we are trying to, so just to kind of recenter ourselves here, right? So I've done a little bit of exploration with this problem at this point, and all of a sudden I'm like, okay, well, let me just remind myself what I'm looking for. We want A111, all right? So if we can find a way to get A111, then we're great. If we can find a way to generate, to figure out what the entire sequence is, or a formula for the sequence, then we'd be able to get A111, and we'll be fine there. So let's talk a little bit about what we would do with arithmetic sequences, right? So I know, for instance, that we could look at the trying to figure out something about the differences between them, right? To get from A1 to A13, obviously I'm going to have, well, I actually have an equation that I can solve at this point, right? Just from what I have here, if I consider the differences, and I could say that, I've got, we'll call A1, let's let that equal X, right? So this is going to be X to the 9th power. Then I could have A13 is going to be X plus 12 times whatever my distance is. And that's going to be to the 6th power. So, okay. And of course, A125, that represents starting from A1 and making 124 jumps, right? So X plus 124 of however many jumps I have, right? So X plus 124D, and that's going to be raised to the 4th power. Now, if you just look at what I have here, you realize, okay, all of a sudden I have more than enough I definitely have enough equations to deal with the variables that I have, right? I can find my first term X, I can find my D from that, right? So again, as I was talking about before, with brute force methods, you can totally make this work, right? You could now take this, solve it for X, solve it for D, and get everything you need. I'm not going to bother doing that here on the screen though, because that's going to be kind of an intense calculation. So what else are we going to do? I'm going to toss it out to the students here. Does anybody see something that we could do? All right. Well, let's explore a little bit more. All right. So one of the things, so we've basically used our log principles to basically get rid of the logs at this point. All right. So we do have some equations here. Yeah. Exactly. So yeah, I mean, you could, right. So Liam's pointing out in the chat that, yes, it's possible, but is anybody going to do that under the time constraints that are available, right? So what we're looking at is at this point we can say we know that we have. So one of the students is pointing out that we have integers, right? So this is a good point about these problems, right? You always want to be keeping in mind the information that they gave you. This is an increasing arithmetic sequence of positive integers. Okay, let's figure that out. So what do we know about positive integers here? First off, if A1 to the 9th power is equal to A125 to the 4th power, then that means that the thing, there's a number that both of these are. And that number happens to be both a 9th power and a 4th power, right? So A1 is both, that the thing that we get in all three pieces of this equation is both a ninth power and a fourth power. Well, A1 to the ninth power, we already know is a ninth power, but we also need it to be a fourth power, right? So A1 is a fourth power. A4 is a ninth power. All right, so now that we're using the information that we have positive integers, right? Be very aware of this in a problem, by the way, right? Anytime you have positive integers in a problem, that's like a gift, right? It's really nice to know that we're dealing with positive integers because you're more familiar with them. They're a lot easier to deal with. You can even do something in order. And that's what one of the other students is mentioning, right? We're going to test small fourth powers here. All right, so we could try that out. Now that we know we're dealing with integers, what if, and let me just throw this out there, right? What if A1 is well, we want it to be a fourth power, right? Well, let's say that A1 is 1. Well, of course, that immediately fails because if A1 is 1, then A13 is also 1, because all three sides of this equality are going to be 1. But they did tell us it is an increasing arithmetic sequence. So I'm not going to let A1 equal 1. All right, so instead of A1 equaling 1, we're going to let it be another fourth power. The next fourth power that we have could be 16, for instance, right? So if A1 is 16, then I've got A1 to the 9th, which is 16 to the 9th, which is 2 to the 36, right? So this would be 2 to the 36. A13 would be 2 to the 36, and A125 would also be 2 to the 36. Okay, if A13 to the 6 is 2 to the 36, that means that A13 would have to be 2 to the 6th, which is 64. And then if A125 to the fourth power is 2 to the 36, then that means that A125 would have to be 2 to the 9th power. All right, so we're going to have 512 there. All right, so at this point we can test that out and see if it works, right? So how do we know if it works? Once again, it's an arithmetic sequence, right? So if I have, so right now from 1 up to 13, I'm making 12 jumps to get a total of going from 16 to 64. That's a difference of 48. I made 12 jumps to get to 48. My difference here is going to be a 4. From A13 to A125, I'm going to have a total of 112 jumps. Whoops, I don't want to write my 112 there. Well, actually, what I'll do is I'll put 112 as a denominator. And 512, to get from 64 to 512, I'm just going to have to subtract 512 minus 64, which I believe gives me 448. Okay, 448 divided by 112, that equals 4. And look at that. I have a constant difference all the way through. So in other words, by letting A1 equal the smallest fourth power I could, again, this is one of those benefits of positive integers, right? With positive integers, you have a starting point. You have a metric by which you can increase them, right? If I wanted to test a bunch of real numbers, how am I gonna choose where to start, right? But if I want to test some positive integers, let's start at 1. Well, 1 didn't work because it's not increasing. Let's do number 2, okay? And it turns out that the 2 works. Now we could have tried another number, right? If I had tried a 3, then A1 would have been 81. A13 would have been 729, I guess. And A125 would have been, who knows, right? 3 to the 9th. That's going to be what, 19,000 something. So, but what you'll see here, yes, that good. So yes, somebody's just bringing that up. If I had tested a number 3, I would be like, wait a minute, that 3 to the 9th is way too big for us to accommodate the kind of jumps that we would need in order to get from 81 to 729 in only 12 jumps, right? So in other words, this thing is increasing so fast that 3 to the 9th is going to be such a huge number. And of course, because 3 to the 9th was way too big, then you could make the case, and you could rigorously prove this sort of thing, but you could make the case that 4 to the 9th is going to be too big, 5 to the 9th, and so on. And so, if for some reason you had just miraculously decided to start with number 3 and then try number 4, you go, oh, wait a minute, those are too big. Eventually you would come to the conclusion that, hey, those numbers are all too big. I'd better try something less than 3. But of course, the beauty of it is, where with especially in this case, it happened to work out that 2 is going to be the one that was what we wanted. And so 2 is the next logical thing to test after finding out that 1 doesn't work. So fortunately, the question writer was merciful to us here and gave us a situation where basically what we have is this. Now, into the problem, then we want to know what A1-11 is. And of course, that's just going to be A1, which is 16 plus 110 of those jumps of 4. So I got 440 plus 16, which is 456. All right. Cool. I guess we can move on to the next one.
I just want to say some few things.
Absolutely.
Yeah, so first of all, this problem, when I was trying to solve it, probably took me the most time on the individual, mainly because I sort of went down the same road as Tim did initially, where, you start with the logs, you get these 2 power equations, and then you get like A1 to the 9 equals A13 to the 6, and so on. And then you try and set up with the arithmetic sequence like he did. First of all, as we saw, it's a 9th degree equation, but also even without that, you have this 124d to the power of 4. That's going to be pretty huge numbers, right? So that sort of tells you it's probably not the intended solution. And at that point, you sort of go back and look at the problem and think of what else you can find, right? So one other thing that I tried initially was, usually one thing I would recommend when people are solving problems is to skip ahead and look at what they're actually asking for, which in this case is A1-11, right? So if you remember what problem number 2 was, it was that linear equation asking like f of 22 minus f of 20. If you started with that first and found an algebraic expression, you would have realized that, okay, I only need the slope for this to actually get the final answer, right? And that's how you would have kind of motivated yourself to go and find that slicker solution. Now, in this case, one thing I usually like looking at with arithmetic sequences is not only setting it up so that it's like x and then x plus 12b and so on, but also looking at their differences, right? So if you look at the difference from A1 to A13, you know that's going to be a difference of 12 times the common difference. And if you look at A13 to A125, that's going to be a common difference of 112d. And then let's say you look from A1 to A111, that's going to be something like 110d. Right. So the reason why I was looking at the common difference was I was hoping that, there would be 2 common differences at least, where one of them is like an integer multiple of the other, right? That was my hopeful thinking. Basically hoping that the problem can be simplified a bit that way. But in this case, as you can see, that is not the case. So at that point was when I went back to the problem and checked, is there any information that I didn't have? And that was, in fact, that I was missing that these were positive integers, right? And I can quickly sort of show the way I did it, which wasn't by doing trial and error, but sort of using the same observations that Tim made in his initial solution, right? So for example, what you realize is, where you had the A1 cubed is equal to A13 squared, right? If you cube, or if you, what you'll realize here is that A1 has to be power of 4, or sorry, you'll realize A13 has to be a power of 6. So let's say this is like n to the 6, right? And the way you realize this is you just square both sides, right? basically because the 3 and the 2 don't have common factors, you know that the A13 is going to need to be a perfect cube as well, right? And similarly from that, you can tell that A1 is going to be equal to n to the 4, right? If you just plug in n to the 6 into this equation, the right side's going to be n to the 12, and A1 is going to be n to the 4. And similarly, with that second equation, you're going to get that A125 is n to the 9, right? So basically, pretty much the same thing as what Tim got, just more generalized for a generic variable n. And here's where the differences helps, right? Because now what you can do is you can look at, for example, A125 minus A13, which is n to the 9 minus n to the 6. And if you look at A13 minus A1, that's going to be n to the 6 minus n to the 4, right? If you take the ratio of these two, that's going to be, well, we know that the first difference was 112D, and the second difference was 12D, right? So the D's are going to cancel. You're just going to be left with 112 over 12. And if you simplify that, that's 28 over 3, right? So one thing that I usually like thinking about with arithmetic sequences is, first of all, my first thought is to look at, A1 and then A1 plus 12D, A1 plus 124D. But as we saw, those numbers got pretty infeasible. The next thing that I usually like thinking about is looking at differences, but more specifically, the ratio of differences between, pairs of numbers in the arithmetic sequences, right? Because when you look at the ratio of differences, then your variables just vanish, right? That's the beauty of the arithmetic sequences. And so you're just left with a fraction. And at this point, you can simplify this out. Something like n to the 5 minus n squared over n squared minus 1, right? If we just divide everything by n to the 4 on numerator and the denominator. And at this point, you can basically finish off the problem with a bit of number theory. And I can see some students are sort of getting what the algebraic approach looks like, right? So basically, it's just I thought it was a pretty nice problem with, a lot of combination of first arithmetic sequences, and then it sort of turned into this nice number theory argument, which you can use to convince yourself that's the only solution.
Yeah, this is a beautifully written problem, and Tanula and I have plenty of experience writing problems, so we know a good problem when we see it. And I think one of the things that's really impressive about this one is how simple it looks on the surface, right? You're like, oh, I'm going to just crank this out, but then you get this this crazy equation that, as Liam said, you're definitely not solving in 10 minutes, and then and so we have a couple of options here, right? I love what you did here, Tanula, of getting rid of the D part, which then effectively gives us a single variable equation. And I see some of the students have done some stuff with that. What I really like is what one of the students did with setting an upper bound based on what we know of this, because that's huge. Because at that point, then it severely limits the search space that we would do. So you could do something like this, or you could just go straight into the guess and check method that I did. But I think one thing that Tanula and I both mentioned that bears repeating is the importance of keeping the question itself in mind, right? You want to be focusing on two very important things. Where are we going, right? In this case, A111. And by the way, one of the things that I was initially thinking about 111 is how far away is that from 125, right? It's 14 away. Is there something with the A1 and the A13, that ends up being a 14? But it turns out that was kind of a red herring, and it doesn't matter, right? Because they could have asked for any value here. Sometimes that number that they're asking for is relevant. Sometimes it's not. But keep the objective in focus, but also keep in focus what you're told, right? Increasing, arithmetic sequence, positive, integers. Those are all vital clues that are going to help simplify the problem for you substantially. All right. Good stuff. Let's move on to our next page here. All right. So number 7. All right. Anybody want to grab this one real quick?
I can take this one.
All right, let's do it.
All right. We need to find the least positive integer for n, for which 123 times 345 is plus n is a perfect cube. All right. So 123 by 345 is a pretty big number. And I don't memorize perfect cubes up until like maybe, I don't know, 20 cubed, 30 cubed. So directly finding a cube that's very close to this and then finding n is really hard. So let's do it a different way. We can see that we can recognize some small perfect cubes. We know that 5 cubed is 125, is also 123 plus 2. Right? And then 7 cubed is 343, which is 345 minus 2. So let's write in terms of the 123 and 345 in terms of a cube plus or minus some offset factor. So 123 is 5 cubed minus 2, and 345 is 7 cubed plus 2. And then we have an extra n, but we'll ignore this n for now. We just want to expand this and see what number we get and how far are we away from a perfect cube, because we're going to get a perfect cube in this expansion. Just from the first term, we get 5 cubed by 7 cubed is 35 cubed. That's exponent rules. Plus 2 times 5 cubed minus 2 times 7 cubed minus 4. Let's keep this here for now because we know that 35 cubed is the cube we're going to be closest to. Simplify, we get 2 times 125 minus 2 times 343 minus 4. That's 250 minus 686 minus 4. That's 250 minus 690. That's minus 440. So this number is actually 440 away from 35 cubed. And so if we have x cubed equals 123 times 345, let's write it like this, plus n. And we know that 123 by 345 is 35 cubed minus 440 plus n, and we want n to be minimal. X must be 35 cubed, because that's the nearest perfect cube we're close to. And that means n must be 440. And we're done.
Cool. I love what you did here, Taman, by noticing that 123 and 345 were both close to cubes. Remember what I mentioned earlier, folks. If you happen to think of Taman's solution and get there, that's great. But remember, there's also other ways to do it, right? So I'll just point out that 123 times 345 is going to be 42435. All right. And one thing you could do is, okay, I know that this is less than a perfect cube. Let's figure out about where we are, right? If I wanted to take the cube root of this thing, if I just wanted to get an approximation, those of you who've done number sense know how to do this sort of thing. First off, we know that the answer is going to be a 2-digit number because we're creating triples of digits starting from the right. So I've got a 042, I've got a 435. So I know my answer is going to be a 2-digit number point something. Obviously, it's not a cube, so it's going to have a bunch of stuff back here. But all we care about is getting close, right? And Taman got us right where we needed to be with that 35, obviously, using some number theory. But again, with just a little bit of extra effort, you can still get this one without the number theory, right? So it's a 2-digit number. What is the cube root of 42? Well, I know 3 cubed is 27, 4 cubed is 64. And so I know my first digit has to be a 3. 42, how's that fall into the 27 up to 64 range? It's about halfway there. So I'm thinking, well, I'm going to test numbers like 35 or maybe 34, right? So at that point, in fact, that's what I would recommend, right? You would start at either 35 or 34 because we're looking for we're looking to bump this thing up as or bump this thing down as far as possible. I would probably start with 34 cubed, and I would at that point, it's just a matter of doing 2 cubes, right? You do 34 cubed and you realize that that's too small. You do 35 cubed and you realize that that works. And the fact that 34 cubed was too small means that 35 cubed is the one you're going for. And from there, if you can calculate 35 cubed, you just subtract your 42,435 and you get the answer as well. All right, let's clear out this one. And who wants to do number 8? All right, I haven't even looked at it yet. All right, go ahead.
All right, so we're given if k is a multiple of 3, let rk be this long sum. We'll get back to that in a bit. For how many values k inside this set, which is all multiples of 3, helpfully enough, is rk a multiple of k plus 1? So we're talking in terms of values of k. Our final answer is a relation defined in terms of k. We're probably not. We could plug in small values. What I want to do instead is just to try go looking for patterns. And if you've done enough of these long sums, you'll recognize stuff like the sum of all k, sum of k squared, and sum of k cubed. Any of which could be quite useful to what we're about to do. So keeping these in the back of our mind, we'll try to express this term here as a polynomial. Just multiply like this, where it's our number in the middle times 1 less times 1 more. Oftentimes, if you feel like you can simplify an expression a little before tackling it, it can help to go with your gut a bit. So we expand this out, k prime here, and then k prime minus 1, k prime plus 1, that's difference of squares. So that's k prime squared minus 1, which is k prime cubed minus k prime. So what we're being asked to add here is the sum from, say, n is 2 to k minus 1 of n cubed minus n. Now, our formulas usually start n equals 1. We don't have to worry about that, though, because if you look at our expression here, if we plugged in a term with 1 in the middle, that would be 0 times 1 times 2, which is just 0. So instead of 2, we'll say n equals 1. At this point, we'll recall our formulas. The sum of n cubed, we'll start with the sum of n, that's the one more people know. Sum of n is going to be our number of terms times our number of terms plus 1 all over 2. And very helpful, the formula for sum of cubes is that same expression squared. All right, so building off of this is we still don't have a k plus 1 quite yet. We'll get to it we could probably get to it by
Okay, Liam, are you still with us? I think your sound cut out.
all right. I think I
Okay, you're
cut
back.
out for
Go
a
ahead.
second. Yep. All right. So jumping right back into it. We're here at these two expressions. So I'll factor out one of these k minus 1 times k terms. And then for the other one, we have k minus 1 times k again, which I'll expand as k squared minus k. And then minus 1. So if we put everything over the denominator of 2, we have k squared minus k minus 2 all over 2. Why is the sum of n cubed equal that? If you want to know how to find it, induction, if you want to know why it matches so nicely with the sum of n, I am not entirely sure. It's a nice coincidence more than anything, as far as I can tell, that we can use to our advantage. But yeah, in general, well, this kind of formula, if you want to show it, you can either show it just by building up from normal sums of n cubed, or you can memorize it if you so desire.
Yeah, let me jump in there real quick. Yeah, like Liam said, you can prove it by induction. So you know, but I think I think the thing we all want to be able to do is kind of internalize it, right? Like why is that? Is that just a coincidence or whatever? So what I'm going to recommend that you do, because we don't have time to demonstrate it here tonight, but there are some brilliant proofs that you can find online. You might even in fact, I remember several years ago, AOPS had like a visual proof of it along the sidebar of their website. You could probably just do a quick search and find some really interesting proofs. There's that'll kind of visually show you why it works, and then that I do find that when you get that visual understanding, it really cements it for you. But of course, for this one, the fact that it's just the square of the sum of the integers is easy enough to memorize as well. All right, go ahead, Liam.
All right, so moving on from here, we have a quadratic. Fortunately, it's easy to factorize. It's going to be, so we'll put my k minus 1 times k here. And k squared minus k minus 2 factorizes out to k minus 2 times k plus 1, which I will write down here, because we have all of this over 4. And now we can see what the question was secretly asking. When is rk a multiple of k plus 1? Well, when this expression is a multiple of k plus 1. Namely, when this part right here is an integer. So we want to know when this k minus 1, k minus 2 expression is divisible by 4. So for that, you can just check modulo 4 to see how it works. It's nothing too difficult. Well, so I'll put k and this expression, which I will call ak. So if k is 0 modulo 4, if it leaves a remainder of 0, we can multiply everything out and see that ak are k minus 1, k minus 2. It's also 0 mod 4. Plug in 1, we get the same thing. Same for 2. And for 3, well, we have a remainder of 3, remainder of 2, remainder of 1. So that's 2 mod 4. Okay, we have a question about what about the terms 2 times 3 times 4, 3 times 4 times 5. So those are all the little terms in here. So if you plug in like n is equal to 3, you'll get 3 cubed minus 3, which if you do our factorization in reverse is 2 times 3 times 4. That's a good question, actually.
Isn't that addressed by the fact that the values of k that they've listed are only multiples of 3 in the first place?
Yes, I think so. That is interesting. So I'll go ahead and admit that I guess I got the right answer the wrong way when I did this, funnily enough. So we just have to make some adjustments. Nothing too difficult. So if we want to add up to k, we'll call k is equal to 3i. No, 3n. I like my n's more than my i's. So what we're trying to solve here is sum from 1 up to n. We have 3. I'll put my m here. Since we're just summing over multiples of 3, as Marcus helpfully pointed out, 3m, 3m minus 2, 3m minus 1 by the same factorization. This one then has to be more carefully expanded out, I believe. That's going to be sum.
So does that, Liam, does that just work out to be 3m minus 1 cubed minus 3m minus 1 using the same logic that you were using before?
It does indeed.
Oh, that's helpful.
Yeah, it's quite helpful. Minus 3m minus 1. Here's where things get a little more persnickety. Keeping the m equals 1 because same rule still applies. Okay, so if we plug in m equals 1, we can see that all here. Now we just have to break down this sum into parts. Just a smidge more cumbersome. You see, when you're scaling like this, you don't necessarily get the same rules you started with. Which is quite unfortunate. I'll be honest, this threw me for a loop a little bit. I have to think about it for a second. If someone else has any ideas.
Yeah, let's get some of the other coaches to jump in here too, because I think we could collectively work this out. So Liam, you're saying that, well, the concern here is that we're not just summing cubes, we're not summing consecutive cubes anymore, right?
Yeah, so that loses the formula we were using previously.
Okay, so it may be that we have to expand this thing out and then just work it out separately, right? So this, so I can factor out a 3m minus 1, and then we're left with what, 3m minus 1 squared minus 1, which is a difference of squares, so we can factor that out further. And everybody else chime in if I go off the rails here, because I want to make sure that I'm oh, this is just going to get us back to where we were. Yeah, I'm just going to get us right back to that factored form that Liam had earlier. So what we might need to do is expand it out, and this thing is going to end up being a third degree polynomial, which, as Liam pointed out earlier, we've totally got all the pieces we need to do that. All right, so I see that Liam is expanding it here. And if I wanted to take the sum of all this stuff from 1 up to n, then that's basically going to be n times n plus 1, n times n plus 1 over 2 squared times 27. And then we just have to add up the squares and add up the individual pieces. And there's no constant term, right, Liam?
Yeah, there's no constant term because of the 3n. So
okay, so then we're going to subtract 27. And formula for the sum of consecutive squares is going to be n times n. Guys, double check me on this. N plus 1 times, is it 2n plus 1?
Yep.
All over 6. And then for this last one, I'll leave it with, I won't simplify the 6 and the 2. We'll just call it 6 n plus 1 over 2. Okay. So we've got that now.
Yep.
All right. And presumably this is going to do something interesting for us, right? In terms of, because like, so I love what you had going on earlier, Liam, and it looked like until we found out we were skipping a bunch of these that we didn't want to skip. It looked like it was very promising. Can we do something similar here?
Almost certainly.
Yeah. And for the rest of the coaches, given the fact that we're skipping some of these, I'm going to ask you all if any of you see a complex numbers solution that we could deal with. And I only mention that because I watched a couple of YouTube videos today that were both dealing with situations where we could hit periodic pieces in a sequence by using complex numbers. So if anybody sees something like that, throw it out there as well.
All right, so if I'm going to expand this, I noticed that
yes,
because of,
the student who asked the question, yes, it was 3 blue 1 brown. I think so I'll, I mean, these are great YouTube channels, so I'll put in a plug for them. I watched one with 3 blue 1 brown that dealt with a problem that was from a USIMO prep book or something. Beautiful explanation of how to use complex numbers along with generating functions for to deal with something about subsets. It was awesome. I then watched a Michael Penn video. Michael Penn's got some great stuff, but sometimes one of the fun things I like about his videos, and I'll talk here while Liam's doing a little bit of calculations. Something I find amusing about Michael Penn's videos is a lot of times he solves things in a very different way than I would. He was trying to calculate the 3030th derivative of e to the 2x times sine of 3x, right? And he's like, oh, here, let's create this matrix that does it, and we'll diagonalize the matrix and blah blah blah. And the whole time I was shouting at the screen, no, use complex numbers for this, right? Because if you just take the imaginary part of of e to some complex number, it would have done it. But yeah, so two different videos I saw today that were both involving complex numbers for solutions to discrete problems like this. All right, so Liam, I see you're doing a bunch of calculations here. Oh yeah, the n, there's an n plus 1 over 4 that factors. There's an n plus 1 over 2 that I see factors out of everything. Did we get did we get a 4 at the bottom of that?
To answer your question, and we have a 4 on the denominator of the cubic term. What would be a 6 if it didn't count out with the 27 on the bottom of the quadratic term, and the linear term has a denominator of 2 or 1 if you cancel. So it all fits over 4.
Oh, right. So, because the 27 cancels with a 3 from the 6, and you can get a common denominator of 4 and factor that out. Okay.
Mhm.
Cool.
So now we've got all of this. I factored it out. Obviously, I could factor out a constant term, but I'm not going to do that right now because as we can see, we have 3n plus 1 here, which if you'll remember, that is the same as k plus 1, which is the thing we're looking for the multiple of. So our question is when does n plus 1, 9n minus 6 leave a remainder of 0, hence, be evenly divisible by 4. All right, now we're back into more familiar territory. Because if we check here, we get n and this term, which I will again call an. And if n is 0, O mod 4, this is 0 mod 4. If n is 1 mod 4, that's 1, 2, 3, leaves 2. So we get slightly different equivalents. If n is 2, then that's 2 times 3 times 18 minus 6 is 12, which is 0. And finally, for 3, n plus 1 is 4, is 0, modulo 4. So the answer to when is this true is anytime except when n is 1 more than a multiple of 4. Now checking for n is easy. That's just all the values of k divided by 3. So we want to know how many numbers in the set from 1 to, and if I do my math here correct, and 74. How many of those are not 1 more than a multiple of 4? Now to count that, I'm going to go up just a little bit more. So I have an actual multiple of 4 I can count from. Since I know that everything is working on remainders, if I throw in 2 more imaginary terms, that'll allow me to get their pattern. So here we have all the way up to 676. Since we're cycling mod 4, I know that 3 out of every 4 of these numbers will give us a value we want. And then, since this is 3 mod 4 and 0 mod 4, or both of those would be correct values if we were counting them, so I'll just take them out afterwards. And now we do some math to make it a bit quicker. Or some of you might know 676 is 26 squared. So I'm looking at 3 times 13 squared, which is 507. Minus 2 is the final correct answer, 505. Which, as I said before, coincidentally, is somehow the same answer you get if you aren't skipping terms like this.
Right, and I think where that comes from is this piece that you did over here, where you figured out which residues worked. You found something similar in the other one where 3/4 of them give you a 0 also, and so that kind of accounts for that, I believe. So cool. Yeah, very very involved problem. Lots of interesting stuff going on. So nice work, Liam. All right, folks. So I see that we've been at this for 2 hours at this point. So I'm going to go ahead and call time on today's meeting. I know we did not get to 9 and 10 or to any of the other questions. If you all are interested in seeing more, we could probably arrange something later this week or next week if you want to go over some more of the problems. But we'll definitely put this one up on YouTube when we get a chance. And thanks for coming out, everybody. And a special thanks to all the coaches who helped contribute to solving the problems today. and to the students who put some wonderful observations in the chat that helped us see some different ways of looking at the problems as well. So thanks, everybody. Take care. And I'll see I'll see you all at practice on Saturday. Bye-bye.